is Soffer Aranov from the University of Utah, and she's going to speak to us about escape of mass of sequences.
Hi, everyone. So thank you very much for the organizers for having me today. So I will say that firstly, this is joint work, based off two joint works. One that is already on arXiv, that's joint with Erez Nesharim and Uri Shapira, and another one that's been ongoing and hopefully will be up on arXiv in a month with Stephen Robertson. Now, I wrote here that this is from the York conference, and that's because I gave this talk at a conference in York last week on Diophantine approximations. But this talk has many different views that you could look at it. I called this escape of mass of sequences, but in the same way, one could also call it escape of mass in Hecke trees, or also one could also call it escape of mass in number walls, or escape of mass of continued fractions. So I'd like to show you all of these ideas. And the first one I'll show is the continued fraction idea. So if we have a quadratic irrational, we know that its continued fraction expansion is eventually periodic. This is a well-known fact from number theory. And we also know that if theta is a quadratic irrational, then p theta is a quadratic irrational whenever p is prime. Therefore, one could ask, let's multiply p theta by p and constantly take powers like this, and then ask, how does the period of the p to the k theta change when we take this k to infinity? So this has been a line of study that has been well studied, and there's several well-known results on this. The first is that if we have p that's a prime, then we could write its continued fraction expansion in this way, and we could ask a few things. So let's just stare at this period. One thing that we could ask about it is how long is the period? So Aka and Shapira proved in 2017 that the length of the period is about p to the k. Sorry, I'll just 1 second open the door and continue. Sorry about that. I'm currently in Europe and don't get used to the fact that there's no aircon here. And then, okay, so now we have this fact that the length of the period is approximately order of magnitude p to the k. Now there's another fact, which is that for every theta, we could also ask what's the largest element in the period. Is it just very long with small elements, or could they get large? So they also proved that the largest element in the periodic part will converge to infinity. Now, you have two quantities that go to infinity, the length of the period and the largest element in the period. So you could ask, how much weight does the largest element of the period take in the entire length of the period? Is it possible that only one element is large and that there's a bunch of small elements, or does the large element just take up a lot of the mass of the period? So to talk about this question, they defined something called escape of mass. And they showed that every quadratic irrational has no escape of mass. That is, if we were to look at the maximal element in the period and divide it by the sum of all the elements in the period, this would go to 0. So now we can talk about how they did this. So to do this, they actually used a different method. They ignored the continued fractions completely and went to dynamics. That is, they used a connection between the upper half plane, the Poincaré section there, and the continued fraction expansion. And then after that, they connected between the upper half plane model and the space of lattices that are defined up to homotopy, which is PGL2R mod PGL2Z. Then the next thing that they showed was that they worked pretty hard using Artin's correspondence to show that escape of mass of continued fraction expansions corresponds to escape of mass of measures that are supported on a sequence of compact diagonal orbits. So this was a lot of words. Let's go a little bit more into the proof. So here, when they did this, they used the homogeneous space, which is X infinity, which is PGL2R mod PGL2Z. And in this setting, there's the diagonal group A, which is in G, and it's just a group of diagonal 2x2 matrices. And we talk about lattices, I said, were nested. The proper way to talk about nested diagonal orbits in this setting with arithmetic meaning is something called Hecke friends. So if P is a prime, we say that two lattices are Hecke friends if one is contained in the other, and the quotient of lambda 1 by lambda 2 is isomorphic to Z mod PZ. So maybe I'll give a quick example of this. One example would be, let's say that lambda is, yikes, let me change it to this one here. So let's say that lambda is equal to gamma infinity times g. Then we could take, this is going to be lambda 1, and we can take lambda 2, which is equal to 1 to g times 1p gamma infinity, like this. So this way their quotient would be isomorphic to z mod pz. And also, we now, this actually defines a tree structure. That is, if we were to take lambda, and then we would look at all of its Hecke friends, and then all of the friends of Hecke friends, this actually forms a tree structure. And this is just a path in this way. Moreover, this tree can be shown to be what's called p+1 regular. That is, every node in the tree has p+1 sons. So now let's talk about some properties of this tree. So let's start with the base lattice, lambda 0, and let's just take all of its friends. That is, all of those that you could reach them through this Hecke neighbor correspondence. Then this forms a p+1 regular tree, which is called TP of lambda 0. So let's now talk about lambda that has a compact diagonal orbit. Now, the reason why we're interested in lambda that has a compact diagonal orbit is that due to Dirichlet's unit theorem, if a lattice has a compact diagonal orbit, one can associate to it a quadratic irrational. And the way that you could do this, I'll show the opposite correspondence, is let's say that theta is a quadratic irrational. Now let's take the field extension Q theta. So we could take the geometric embedding sigma from Q theta to R. And then we could look at sigma of z theta. And this is going to be a lattice. So this is going to be the following lattice. So let's say that theta has characteristic polynomial p theta, that its roots are theta 1 and theta 2, and the embeddings are sigma 1 and sigma 2. So these are the two embeddings. So this goes from here to R2. So here we could look at sigma 1 of theta 1, and then here sigma 2 of theta 1, sigma 1 of theta 2, and sigma 2 of theta 2 times Z2. And this here would be a lattice that has a compact diagonal orbit due to Dirichlet's unit theorem. And moreover, since it has a, so this is on the number theoretical side. Since it has a compact diagonal orbit, then it's known that it will support an A invariant probability measure that we denote by mu of A lambda 0. Now, since every one of its friends is going to be something, a finite index inside of lambda 0, then this means that all of its Hecke friends will satisfy the same properties. Rather now, if lambda is in this tree, then it will correspond to a different quadratic irrational, and it will support a different A invariant probability measure. So the entire moral of the story here is that instead of studying the escape of mass of continued fraction expansions, they actually studied what happens to these probability measures and what could be their limiting measures or distributions when they take these along a specific branch in the tree. So let me explain what happens here. Here, a branch in the tree would be a path or a geodesic in the tree. So we have all sorts of branches that they zigzag back and forth. And for example, we have this red branch here that maybe you first start out zigzagging, but then at some point you always take right. At every single stage you take right. And that corresponds to choosing a certain diagonal lattice that moves between one of these lattices to the other one, like a certain diagonal matrix. So now when we do this, these branches where at some point you eventually always go right are called rational branches. So what they did was that they just looked at the measures along these. So this branch here has measures mu lambda 0, A lambda 0, mu A lambda 1, C, and so on and so forth until you have here, and then you could look at these limiting measures, the limit of mu A lambda n, C, as n goes to infinity. And what could these limits be? And that's how they studied these continued fraction expansions. So now let's define a little bit about how we can study these. So in this case, we say that probability measures, these are all probability measures, they naturally should converge to a probability measure, but they sometimes may not if, for example, the space of probability measures is not going to be closed in this topology. And this is what happens here. So here we say that the measures, they exhibit C escape of mass if every accumulation point of these measures gives mass to the homogeneous space of at most 1 minus C. Now, what they showed was that the escape of mass of p to the k theta would correspond to escape of mass of these measures. So the important thing that they showed here was that inside this Hecke tree, all branches, besides maybe 2 branches, and this is under some very specific algebraic condition, do not exhibit any escape of mass, and moreover, they equidistribute. This means that if one were to look at this thing here, 1 over n plus 1, the sum of mu n c, where n goes from 0 to n, is going to converge to the Haar measure on x infinity. So this was what they showed, and that's how they showed this escape of mass of continued fraction expansions. And what I do in my research, or what I did here and in general, is I asked what happens if one were to replace R with the field of Laurent sequences over a finite field FQ. So in this setting, we have to explain who are our players. Instead of R, we will be discussing the Laurent series. So this is going to be our analog of R. And instead of Z, our analog is going to be the Laurent polynomials. The Laurent polynomials, they have finitely many powers, and they're all positive. And then the Laurent series, they could have infinitely many powers, but definitely finitely many positive powers. So just like in the real setting, if we have theta that's a quadratic irrational, then in general, we have that it's a quadratic irrational if and only if its continued fraction expansion is periodic. So in the exact same way, we could ask, how do these continued fraction expansions distribute? And another thing is that in the continued fraction expansion, we have here the elements of the polynomial. So now let's talk a little bit about this distribution and what is known. So firstly, let's write the continued fraction expansion of t to the k theta to be in this form. So let's say theta is some quadratic irrational, and then therefore t to the k theta is also a quadratic irrational. So it has a periodic part here. And now it has this part over here. So we could write it like this. And now let's see what is known. So the first known result, which is an old result by Dematan and Toily, which they proved using combinatorics actually, says that the maximal degree inside the period will converge to infinity. Okay, so now we could also ask about the length of the period, which was what was studied in the Aka-Shapira paper. And this was proved both by Kemarski, Polan, and Shapira, and later on by Polan and Shapira, who showed that the length of the period is infinite. Not only is it infinite, it's order of magnitude k. So this seems very similar to the real situation. On the one hand, we have that the degree goes to infinity, or like some way to bound the norm of the largest element goes to infinity. And on the other hand, we see that the length of the period also goes to infinity. So we have 2 infinite quantities. And we can ask, how do we compare between them? So let's see how they chose to compare between them. To do this, Polan and Shapira, they defined what's called the Kn escape of mass of theta. So this is defined to be, this here should be a K, to make it clear. So this here is defined to be, in the denominator, you have the sum of the degrees that you see inside of the period. And in the numerator, you sum up only the degrees that are larger than some height n. So in this way, if you have a degree that's very small, you're just going to kill it off. So they just looked at this thing here. And what they showed was that there is some uniform C that depends on theta, some C theta, such that the limit as n goes to infinity over the lim inf of k goes to infinity of ekn is greater than or equal to C. Now, firstly, this is very different from the real setting where this limit was 0. Another thing is that we could see here, let me explain what this expression means here. This expression explicitly is like saying, let's count the asymptotic proportion of degrees inside the periodic part, which are very large. And they show that this asymptotic proportion is large, is non-negligent, unlike the real situation. So one can ask, why is this? Because indeed we do have these two results that seem very similar. So those of you who are very sharp may recall that in the real setting, we had that the length of the period was exponential, whereas here it's linear. And this is actually one of the main causes of this. So now I can dive a bit more into the method of proof, since this may shed light a little bit about more what happened. So again, in this setting, we use the Hecke trees that we defined earlier, but only this time for these lattices. That is PGL2 lattices here over where we have here PGL2 Laurent series, mod PGL2 Laurent polynomials, and then they again studied the escape of mass along the branches. And then instead of Arden's results that work in the real setting, there's an analog in the function field setting, which is results by Frédéric Pollan, which connect this the escape of mass in the Hecke tree to the escape of mass of the continued fraction expansion. Okay, so now after they showed that there is some escape of mass, they actually conjectured that there's full escape of mass. That is, they conjectured that if we look at this expression above, one can take this to be equal to 1. If you do not understand it in that way, they conjectured that if we were to look at certain branches that are called rational branches, that mu of a lambda n will converge to the 0 measure. So I'll explain a little bit about the history behind this conjecture. So this conjecture was made because Pollan and Shapira, they checked this conjecture for some specific examples of quadratic irrationals, and they seem to exhibit full escape of mass. After this, Uri Shapira, as well my PhD advisor, he gave me this to prove this conjecture. And me, as a very ambitious PhD student, I tried very hard for a very long time to do it, and I actually failed, very badly failed. Rather, I disproved this conjecture. In every characteristic, we showed that for all p's, we could find an explicit counterexample that's in the field of Laurent series over fp that firstly does not satisfy the conjecture. That is, it exhibits partial escape of mass. So if one were to take this escape of mass here, then this would be equal to, we found in our example, 2/3 when p is equal to 2, and this is the result with Erez Nesharim and with Uri Shapira. And the ongoing work with Stephen Robertson handles every single odd prime p, and it shows that there we have partial escape of 2 over p. So you may say now, we're happy, we disproved a conjecture. But when a conjecture is false, a good thing to do is to check how false was it. So we decide to do something else and just replace this lim inf over here with lim sup and see what happens. So it turns out that at least for these particular examples, the Kemarsky-Pollan-Shapira conjecture was not super false, in the sense that if one were to replace lim inf with lim sup, we actually get 1. That is, maybe maybe some sequences exhibit escape of mass that's less than 1, but if you were to take a specific sequence of k's, then you could still obtain this upper bound 1. And not just that, we found something stronger, which is that for almost every subsequence that's increasing, we could get that this is 1. So many of you may not like that I said for almost every subsequence, because this is a subsequence of natural numbers, and therefore you could say there's no Haar measure there. And you would be right. So the correct notion of genericity, of being generic in this setting, would be upper density, which is large. So here, this expression says that the density of the set of all k's such that the case escape at point n of theta is going to be less than 1 minus epsilon is 0. So that just says that up to a density 0 set, we'll probably always have this full escape of mass. So up to now, many of you may, as people who like combinatorics, may not understand why I came to this talk. And now I'll explain the connection to the combinatorics on words. And this is the method of proof. We proved this conjecture not using Hecke trees and not using continued fraction expansions, rather using something else called Henkel matrices and diagonally aligned number walls. So here, if we have some subsequence of FQ, which you could view as an infinite word, we define the KM Henkel matrix to be a square M by M matrix that starts with theta k in this coordinate here. And then after that goes theta k plus 1 up to theta k plus m. The next row is just a shift of the first row, and every row is simply a shift of the previous row. So now these matrices, we want to take their determinants and then we put them into a double-sided array, which is called a diagonally aligned number wall. Now there's this diagonally aligned here, which just means that it's faced a certain way that enables us to see the dynamics more easily. But in any case, this is how it's defined. So the diagonally aligned number wall is going to be a block. So it's going to be a matrix where above the diagonals you have 0. On one of the diagonal, which is n is equal to m plus 1. So this is one diagonal above it, we have 1s. And then after that, we have whenever n is equal to m mod 2, it's 0. And otherwise, we get the value of the determinant of the Hankel matrix that begins at m minus n over 2 and by m plus n divided by 2. So this definition is kind of funny, but we did this definition actually because this is how we could see the dynamics. Usually number walls are not like this. Rather, this line that I drew over here would usually begin at the top and it would be like this. Yikes. And the reason why we did this drawing is actually due to dynamical reasons, but many prefer to do the regular number walls. So now I'll explain why does this relate to everything that we talked about earlier. So this goes from the Diophantine properties of these Hankel matrices. So now let's start with some number, some Laurent series, theta, and its coefficients are theta n t to the minus n. And let's write out its continued fraction expansion, and let's assume that n is some polynomial of degree h and write out its coefficients. Then in general, if you were to have a Laurent series, sum n equals negative infinity to n of a n t to the minus n, this here would have the norm or absolute value q to the power of n. Sorry, this is without the minus, so this is just going to be q to the power of n. So that would be the norm. So now we see that if we want the norm of the distance of n theta from 0 to be less than q to the minus l, then what would we need to do this? We would need to ensure that if one were to write n theta as a Laurent series, let's write this Laurent series out as a sum of ci t to the minus I equals 1 till infinity, then one would need to ensure that C1 up to CL are all equal to 0. Okay, so now we see that we have to just compute these CIs. So these CIs, one can compute them by simply using products of series. And this is something that we all know from calculus, that CI will be of this form over here. So this is going to be theta I times n0 plus theta I plus 1 n1 up to plus theta, this here should be I plus h and h. So this is going to be this form. Okay, so now we have a bunch of different equations. Let's put them all into a matrix. This is actually a linear system. Here we have for theta 1, we get this exact row. Theta 1 up to theta h plus 1 times n0 up to nh should be 0, and so on and so forth. Okay, so now we see that some type of Hankel matrix, only now they're no longer square, times some vector brings a 0 vector. So this gives us a non-trivial solution to this system of equations. Okay, so this is how we can connect these Hankel matrices to Diophantine approximations. Now, I wrote here this continued fraction expansion, and let's explain how this comes in, because this is how we began our whole story. So here we have that we know that Pn over Qn, this is what happens when you take the continued fraction expansion, you stop it at the point n. So this is what's called a convergent of theta. That is, Qn theta is the best approximation of theta in the sense that there exists some L such that the distance of Qn theta from 0 is less than q to the minus L. But if one were to take any degree that's smaller than the degree of Qn, then we would have to have an inequality in the other direction. That is, we would not be able to beat this approximation here. Okay, so let's reinterpret this fact in terms of Hankel matrices. This fact says this. Let's take M to be the degree of Qn. So using what we said earlier, we can find some L for which the Hankel matrix that's going to have L rows and M plus 1 columns around of theta times V, which is going to be the vector that contains the coefficients of Qn gives 0. But then on the other hand, that's the condition 1. But on the other hand, for condition 2, if one were to take one order less, that is, if we were to take one column less, then we'd get that this is always non-zero. So now using the theory of Hankel matrices, one can show that the M by M determinant of this, the determinant of the M by M Hankel matrix would be non-zero. Are there any questions until now? Maybe it's a good point to stop and ask if there's questions. Okay, then. So now we get this. So let's now summarize everything that we said into our continued fraction. So let's let t to the k times theta be, this is its continued fraction expansion, and let's take the convergence. Then we obtain that f in the mkth coordinate, which is going to be this guy over here, only replace this 0 with the k, would be non-zero if and only if there is some degree n for which the degree of q and k is equal exactly to m. So that's how we connect this to this escape of mass problem. Okay, so now let's take everything that we've said and translate the property of escape of mass into a Hankel matrix formulation and a number wall formulation. So now let's just translate everything. So instead of taking here this maximal degree, every time we see this degree, we're just going to replace it with another expression. So as I said in the previous slide here, we said that fmk is non-zero if and only if there's a degree of a convergent, of a denominator of a convergent, which is equal to m. But what is this degree of this denominator of this convergent? So note that the degree, that due to the theory of continued fraction expansions, the degree of Qn plus the degree of An plus 1 is equal to the degree of Qn plus 1. So therefore, if one were to look at the degree of An plus 1, it would just be the difference between the degree of Qn plus 1 minus the degree of Qn. So we will just use this and replace everything in here. So here, if one were to take, so let's just look at this Kn escape. So this is, I'm just recopying this definition. This is just this maximal of these two, but this is equal to the degree of Qk I plus 1 minus the degree of Qki. Okay, so now what does this mean in terms of the diagonally aligned number wall? Recall that we said that the jth non-zero's coordinate inside of the kth column of the diagonally aligned number wall is exactly going to be this degree over here. And therefore, we could just replace this with this expression here, where this expression here, this hkj, is actually the jth non-zero element inside of the kth column when we go straight down. So now we got a new theorem that does not have continued fraction expansions, and it also does not have any Hecke trees, and it just relates to number walls. And what does it say when we want to go down to it? It says that escape of mass of the continued fraction expansion, it would correspond to the proportion of large distances between non-zero coordinates inside of basically the columns. So maybe this is kind of hard to understand without a picture. So let's now look at a picture. This here was our counterexample when we take q is equal to 2. So when q is equal to 2, this is our counterexample, which is the well-known Thue-Morse sequence. Yikes. I will try to move this a little. Okay, so let me try to move this. Come on. Okay, I'll try that again because I like to show this with the ruler. Yes. Wonderful. Okay, great. So this is what I wanted to show you. So what I'd like to do is that now I'd like to show how exactly can we compute this escape of mass. So the escape of mass, let's say that this is the jth column, would be if we were to look down this line and we would just count the proportion of white, unbounded white parts inside of this line. And that would be the escape of mass. So that's exactly what that previous theorem that we're to get to says to us. And now, for example, let's just draw a few lines just to see some examples. So for instance, let's take the line that goes down here. So this is right in the middle of the largest triangle that you see. And if you go right down the middle, you could see here this partial escape. Why? Because outside of this big block here, which does not take out the entire period, we see that we have no other white. So the only part that would contribute to the escape of mass here would be this part. On the other hand, if we were to move a little bit, let's say we were to take something here, then we would have more contribution of the escape of mass, and therefore the escape would be higher. So this was actually how we found our counterexamples in this case, by just studying these types of rows, and by studying these types of columns and looking at what could happen in these zero blocks. Moreover, so let me show you some more examples of this. So for example, if one were to go along this here, then over here, we wouldn't have any contribution, but then this part here would contribute a significant amount, and this part here would also contribute a significant amount. So that would be how we'd study it. Now, let's talk about these zero blocks. So it turns out that there are very well-known results on these zero blocks inside of these number walls that, as you see when I say a zero block, I mean this white diamond. In this picture, the white is the zeros and the blacks are the ones. Results that are well-known on this. So there's several well-known results. The first result is that if theta is a quadratic irrational, then it must contain zero windows of unbounded size. This wasn't the old result by Dematan and Toily, and this in particular implies that every quadratic irrational exhibits some escape of mass. And it also implies in particular that this, so this was exactly what they showed to do this. And also, so you could ask, is this even a remarkable property? If I were to take some random number wall of any sequence, would it always have very large zero windows as we saw in that picture? It turns out that this is false. And this is actually a truly remarkable result. So in a seminal paper, Adisim Nesharem and Lanen, and later on Robertson and Garrett Robertson, they proved that you could find diagonally aligned number walls that only have zero windows of bounded size. And this was actually a very seminal paper. And the reason why it was so seminal is because it relates to what's called the Tiadic Littlewood conjecture, which was also conjectured by Dematan and Toily in the same paper. So in general, many of you may have heard of the very famous Littlewood conjecture, which talks about joint multiplicative approximation of numbers, basically, and this is a very famous conjecture in number theory. So this was a very difficult conjecture that's been proved to be true up to a set of Hausdorff dimension 0 by Einsiedler, Katok, and Lindenstrauss, but it has not been able to be shown that it's always true. Now, to tackle that conjecture, Dematan and Toily proposed an easier version of it, which is called the Tiadic Littlewood conjecture. And it says that for any theta, that's a Laurent series, if we were to look at the infimum on all n's that are Laurent polynomials of the norm of n, the distance times the Tiadic norm of n, times the distance of n theta from the polynomials would be equal to 0. If you do not like this formulation here with this Tiadic norm because it makes you feel uncomfortable, you could look at this formulation here, which is just going to be the norm of n times the distance of n t to the k theta from the polynomials, where k can be anything. So they claim that this is 0. Another way of saying this is that there is no number that is uniform, that its shifts t to the k theta are all uniformly badly approximable. Now, Now, what happened was that Adisim, Neshrim, and Lanin, they proved that theta satisfies the t-adic Littlewood conjecture if and only if its diagonally aligned number wall has zero windows of unbounded size. This conjecture was believed to be true, and therefore it was quite remarkable when they discovered a counterexample for this. And the original counterexample by Adisim, Neshrim, Lanin was when when the ground field FQ is actually F3. Later on, Robertson and Garrett Robertson generalized this for other ground fields, such as 3, 5, 7, 11, and 13. And it's now believed, at least unofficially, I believe this, and many other people believe this, that this conjecture is false in every odd characteristic. Okay, so now let's go back to a little bit about what happened here for our proof of the escape of mass. So to prove this escape of mass, what we did, and this is actually a very similar method to the methods that were used in all the Littlewood papers, is we first defined a tiling from some small set of tiles to matrices over that set of tiles. And then after we did this, we defined a coding that simply took our picture that we got to some P by P matrices with only two tiles, which are black and white, or if you want 0 and 1, and this gave us a matrix F. So up till now, I had no quadratic irrational, I had no escape of mass questions. All I have here is some geometric construction of a tiling. Now we could ask, why is this even related? And that would be a good question. So we prove that this structure that we got, this matrix, it has the exact same structure as the diagonally aligned number wall of our counterexamples, which are either the Thue-Morse sequence or the P-Cantor sequence. And this is one useful thing about these diagonally aligned number walls, which is that they have a very particular structure that many of you may have seen, such as that the zeros must appear in those blocks. Okay, so now we got to this stage. We found out that we're working with the correct object. So the next thing that we have to do is that we have to prove our theorem. So to prove our theorem, we first use the self-similar structure of this tiling and coding to find the exact sequences inside of this matrix that exhibit the exact minimal amount of escape of mass that we want, which is 2 over P when P is odd and 2/3 when P is even. And we prove that this is indeed the minimal amount of escape of mass that we're interested in. And then we do the same thing to find the sequence that exhibits maximal escape of mass. So this would be the escape of mass 1. And we can give an explicit description of all of these sequences for all of our examples. Now, the last thing that we do is that for the generic escape of mass, we use a different method. Instead of finding explicit examples, which one cannot do when you're talking about generic sequences, we use Markov chains to describe the tiling, and then we show that the density of the sequences that do not exhibit full escape of mass is 0. So this has been fun, but let's go to the most fun part for many people, which is the pictures. So here, this is the tiling that we use that generates the diagonally aligned number wall of the Thue-Morse sequence. Now, from a different point of view, I could have started this talk without any of the dynamics and just talked about an just finding an automaton which generates these Henkel matrices of the Thue-Morse sequence. In terms of this history of this, so Aluce Perrier, I believe, when proved back in the 90s that the Henkel matrices of the Thue-Morse sequence form an automatic sequence. And in this point of view, we actually fill in a gap by showing what is the exact automaton that generates the sequence. And this automaton comes from this here. So here, this is the tiling that we use. In this tiling, you can maybe see some of the structure. You can see here that all of these white windows, these are zeros. And you can also see that these windows have a very particular structure. That is, if you were to look at its frame, it will be red, pink, rose, and yellow. Now let's look at one frame above this. So here we have shades of teal, shades of purple, shades of green, and here we have shades of blue. And they are all identical in this sense. And also we see that this top part here is all red, which corresponds to ones. And this part here, is going to look like the through more sequence. That is, if this light blue is 0 and if this dark blue is 1, then we have 0, 1, 1, 0, 1, 0, 0. And this is exactly the through more sequence. So this, in this sense, is how you could see the structure. And all of this is part of the structure theorem for these diagonally aligned number walls. Now, once we have this tiling, which we produced, which we were able to find by first producing, using some algorithm, the exact number, diagonally aligned number wall of the through more sequence, and then after that, trying to find the tiling by hand, we code this tiling by taking every 2x2 matrix here to a 4x4 matrix with only zeros and ones. So after doing that, we get this picture here, which we just then after that prove that this is exactly what we need. And this is exactly the diagonally aligned number wall of the through more sequence by using our structure theorems. So now let's go to an example when p equals 11. So here we did not do a diagonally aligned number wall. If it were diagonally aligned, one would have to twist their head by 45 degrees like that to make it diagonally aligned. So maybe this is a good time to tell an anecdote about the diagonally aligned number wall versus the regular number wall. So the reason why we did the through more sequence as a diagonally aligned number wall is because before I even began working on this with Erez Nisharim, who was my coder on this project, he was discussing this project with Elon Lindenstrauss, who is a very distinguished mathematician, and he was showing him pictures of number walls like this. But Elon, as a dynamicist, wanted to see the dynamics of this, and the dynamics become apparent in this picture when you look along the diagonals. So Elon did what any person would do to look at the dynamics, and he turned his head like that by 45 degrees. We started to feel sorry for him, so we just turned the number wall, and then we got this picture, so that he would not have to twist his head and hurt his neck too much. So that's why we have the diagonally aligned number wall here, and also the dynamics are apparent when moving along the columns. When moving along the rows, we believe that there's another dynamical system there that we're trying to understand a little bit better. Now, this would be the regular number wall, and this is the tiling that we used for the 11 Cantor sequence, which is our counterexample when p is equal to 11. So let's just see some pictures here. So here, for example, instead of looking along the rows, one would have to look along the diagonals. So let's do this at 45 degrees. So for instance, if you were to take this diagonal here, you could see in this picture, the red corresponds to the zeros. So if you were to take this diagonal here, then you see that there's no zeros, but this is because it's a partial picture. If you were to continue this picture for infinity, you would eventually hit a very large zero block, but you see here that this is a partial escape because you have a very large segment with no zeros. On the other hand, take this part over here. Here you're going to have very many segments of zeros, and therefore here this would be the full escape. And then if you were to take something intermediate like this, then you'd have something between the lowest partial escape and the full escape of mass. So that's how we did something with these. And then for this, the way that we coded it is that everything that was red, we just coded to zeros, and everything that was not red, we just coded to ones. And that's how we did the coding. So we did a lot of work on this, and there's still plenty more work to be done. And I'd like to propose some questions, which I would be very happy if anyone in the crowd would think about them or would like to discuss them. And some of our questions are, firstly, we showed that this Kamirsky-Polanyi-Shapira conjecture was not completely false, at least in these settings, at least for these examples, in the sense that we found that indeed the zero measure was an accumulation measure for these particular sequences that we found. And not just that, you could have certain sequences that exhibit full escape of mass. So we could ask, is this always the case? Will there always be some sequence that exhibits full escape of mass? We actually believe that generically we should have full escape of mass, and that these subsequences that are this counterexample should not be common at all. So another way of saying this in terms of the Hecate is that the proportion of n such that mu of a lambda n gives mass to the entire space of lattices of more than epsilon would converge to zero as n goes to infinity. Now, we can ask another question, which is the astatic case. So recall that here, in terms of the continued fraction expansion, we talked about escape of mass of this sequence. But we could change the sequence to taking escape of mass of nu k times theta, where nu k is just going to be a sequence that's where nu k is this guy over here, which is given by a product of primes, where these primes belong to some finite set of polynomials. Let's say even if you took 2 or 3 polynomials, it would be interesting. And maybe the context of this is that originally the Aka-Shapira paper discussed the astatic case, whereas the Kemarsky-Polan-Shapira paper came to say here in positive characteristic, it's different than the real case by giving a specific example with just one prime. But maybe with many primes, the behavior could be different, and it would be interesting to see that. Now, another question is we worked very hard to talk about rational branches in the Hecke tree, which are those branches that at some point they always take right because they correspond to the Diophantine picture. But what happens if one were to take a generic branch in the Hecke tree that is not necessarily rational? So it's actually believed by Kemarsky, Polan, and Shapira that these branches should equidistribute, but no one has yet proved that. Now, another question in the dynamics sense is what happens to the building of PGL3? And in this case, this is another question here. This is a deep question, is firstly, what would be a number theoretical question that would correspond to this? Now, there's some more questions about this in the numeration side of it or in the automaton side of it, such as that rise from something else, which is we defined here, we worked pretty hard in our method of proof to find a certain automaton that generates the number walls of these sequences. And note that another thing is that our original sequences, they are automatic sequences. One way to see it is using Christoffel's theorem, which states that a sequence is automatic if and only if the corresponding Laurent series is algebraic. And indeed, this is the case for quadratic irrationals. So what do we have here? We have here a sequence whose number wall, we have an automatic sequence whose number wall is also automatic. And not just that, the sequence is P automatic and its number wall is also P automatic from the way that we constructed it. So one can ask, is this always true? And this was conjectured in a paper by Stephen Robertson, but I believe it was informally conjectured, at least I heard it from correspondence from Fosdan Adissim, that this should hold. It would be very interesting to see this as well. Okay, so now that I have all the questions, I would like to firstly say thank you very much and enjoy a picture of me and my son working on an earlier version of this tiling last year. So this was a very old version. And thank you very much for having me.
Thank you very much. Does anyone have any questions? How did you think of using the 2A Morse sequence for this construction?
Okay, actually, I wouldn't say that we really thought of using the Thue-Morse sequence for this construction. Rather, it's in a way one of the simplest sequences that you could define. So what happened was that first we were thinking of let's just generate the number wall of it, more like Erez just wanted to generate the number wall of it to understand it. And then after doing that, we found out visually that this seems to be the correct counterexample, and it turned out that it was.
Okay.
I have a quick question.
Yes.
Yeah, Jeff.
Yeah, well, maybe I already asked you this before, but my memory is not so good these days. There seems to be examples of very simple morphisms on 4 letters for which the infinite sequence generated has all Hankel determinants of all orders starting at every position non-zero.
Yes, it could be. I don't know that, but
Yeah.
sure.
Is there anything from your work that could be used to like try to attack it for a specific example that I have in mind?
Okay, I'm not completely sure. One of the biggest, I would say, downsides of this line of proof, in my opinion, is that whenever you work with these proofs, we have to work very, very hard to prove something about one specific example because it all relies on the structure of the sequence and defining a very particular morphism for a very particular sequence. Though the work with Stephen is maybe the first time that somebody has generated infinitely many number walls at once, but they are still very similar number walls. So it could be interesting to try at least this method for this, but I would say that this is one downside that I am still trying to overcome when it comes to proving generic results about these.
Okay, thanks.
Are there any other questions? If not,